Can you hear me now? We're gonna get started here in a couple minutes. If you guys want to find a seat, there's a couple seats up here up front. We're gonna be about 2 minutes, and we're gonna start. So if you want something to drink, please get it now, and then we'll be ready to start.
Hello. Hey guys, don't mind taking a seat. We can get started. So thanks for once again coming to tonight's Spark meetup. A great presentation today. So before we get started, just a few quick announcements. So September 15th, we're doing a Google BigQuery meetup at the Rubicon project. So if you look at the Big Data user group, you can see more information about that. End of September is Hadoop World. If you're going down, there's a discount code on the meetup pages. You could use that to get 20% off. And in October, we're also doing a Google Big Data Day kind of thing where Google is going to be hosting an event at the Google Venice office. So we'll post information about that shortly so you guys can come take a look. With that, I'm going to hand over the microphone off to Jack. Again, I just want to thank Politica and Cloudera for helping host tonight's event.
Thanks, Sebastian. Welcome to Playtika Santa Monica. I'm Jack Kuchenkoff. I'm the VP of Big Data here. We've had a couple events in partnership with Cloudera and with Sebastian, the Spark user Sqoop. Want to welcome everybody here. We're going to hang out after the end of this and talk technical about Spark and Kafka streaming and a few other things. If you're interested in learning a little bit more about kind of what we do, you can kind of follow me on Twitter, and you can see some of the new stuff that we're doing with like parallel streaming, processing, and Vertica and such. We are Playtika. We're a social gaming company. Number of studios that we have: World Series of Poker, Bingo Blitz, and Slotomania free-to-play games. That's kind of what you see all around here. This is Litzy, our bingo mascot here, in case you're wondering what that's all about. But without further ado, I'll go ahead and hand it off to Cloudera and Marie, who's going to talk about Kafka and Spark, which I'm sure we're all interested in hearing about. So wherever he is, there you go.
Good evening. First of all, thanks, Jack, so much for hosting this. Interestingly enough, I wasn't expecting LA to be so hot. I guess I was wrong, right? Coming from SF, it seemed a little hot. SF was like this 2 weeks ago, though. Okay, so before we start, how many of you have used Kafka? Okay, that's a good number. And how many of you have used Spark? Almost the same people, which is pretty interesting. And how many of you have used these two together? Okay, like 20%. Good thing I'm talking about it today, and stuff that you may or may not have used or read about. So my name is Shreedharan. I have been at Cloudera for about 3.5 years, almost close to 4 years at the end of the year. So I have seen Cloudera grow from a 100% company to close to 1,000, with pretty much no customers to a whole lot of customers now. So from what I've seen, what has happened in the last 3 years is the amount of data that people have and people want to process has increased a whole lot. And that's the whole reason there are big data user groups all over the place, right? So one of the major differences we see between 2012 and 2015 is that 2012 was a time when people did not consider ingest to be a big problem, right? Oh yeah, I can write it into files and do an HDFS code and go into HDFS. While 2015, everyone knows that's actually as big a problem as processing. The best thing to do is to actually process while you ingest, so you can eliminate a bunch of your data before it actually hits your storage systems, which is what we would like to do using streaming platforms, right? So streaming platforms come in a variety of ways, but today we talk about Spark, specifically Spark's streaming system. So Spark streaming is a part of the Spark assembly, which you could download from Spark.Apache or from the CDH distribution. So Spark streaming is actually a library. We'll talk about it in a bit, but let's get started. Really, why do we need real time, right? Actually, the thing is we need real time for a bunch of things, but we don't actually get through real time. Any system you're talking about is not true real time, it's near real time, right? There's a network delay all over the place. You're writing stuff over a network. If there's zero network delay, hey, I think we'll be in a different place. We wouldn't have to do all this processing and stuff like that if your network delay is zero. So there's almost always going to be a network delay. There's going to be delays in your software. Any fault-tolerant distributed system you use, failures will lead to the system giving you degraded performance for how much of a small a time it is. It will still give you some degraded performance during some failover, some data being picked up from a different replica, things like that. So you're going to see delays everywhere. So you see near real-time processing of data. So the problem here is to how to get that near to be as small as possible. Process the data as quickly as it was being generated. So data is generated, process it right now. Can that difference be less than a few milliseconds, or does it have to stay at hundreds of seconds, right? That's the difference you're talking about. If you're talking about MapReduce, you're looking at several hundreds of minutes, probably. You'll write the data out, wait for all the files to be rolled, and then move them into a directory and process it. But can you reduce that to a matter of a few seconds? Can you process it as soon as it comes in? So that's where streaming platforms come in. Streaming platforms can help you process as much of the data as it is becoming available. The advantage of using streaming platforms is that often even more than just doing large amounts of processing in batches and things like that, the advantage is that you can eliminate a lot of the data or reduce the amount of data that you're going to send to your archival storage or your storage system and then process it over time. Think about it, right? This is the number of things from which you're receiving data. I copied this from a product manager slide. I didn't even read it. But the idea is that look at all this. This is the number of things that's sending data. You know, there's this company right next to Cloudera's offices called Nest. Nest is actually, they manufacture thermostats and things like that. These things keep sending real-time information to the servers, and it does a lot of machine learning, whatever, and then updates its algorithm in real time. The amount of data that these things collect grow over time, and if they start selling more and more of these devices, the amount of data is growing exponentially. At that point, it is practically impossible to store all of this, even if you're being funded by Google, right? So the problem here is to process and save as little data as possible, process as much of the data, save as little of it, so that this little data which you save can be used later for further processing using your standard MapReduce applications, your warehousing systems, things like that. So how has big data evolved to solve this specific problem, right? Earlier, big data was always about being able to process a lot of data. Hey, MapReduce job, it can process a massive amount of data. As long as you have space on your cluster, throw it at the MapReduce job, it will process, right? It wasn't an issue at all. You didn't have to think about it like, oh, is my Teradata appliance becoming full? Can I afford to actually process this? Do I have to pay $1 million to Teradata just to process this one thing? Earlier, that was the case. Then it became MapReduce, where you could put in a bunch of machines and just process it. Now, what happened with that? Hey, the data is there's so much of data that buying those machines are themselves becoming more expensive. So now you want to process it as soon as you can. So that's where we recommend doing streaming, right? If you can process it as soon as you can, you're getting results, you're getting value out of your data as soon as it's being processed, which could mean very, processing every 2 seconds. By default, Spark streaming, every 2 seconds is when it actually processes the data that comes in. So the difference between actually having value out of your data and having value out of your data as soon as possible is usually pretty big. Now, how do streaming architectures usually look? I tried to justify that you sometimes need a streaming architecture, right? But how do they really look? Streaming architecture is not like MapReduce or Spark batch processing in the sense that you only need Spark and just the data on an HDFS cluster somewhere. You actually need another component which you can fall back to. That's your ingest system. So you almost always want to read data from an ingest system, simply because of the fact that if for some reason you can't process the data, right? Your Spark processing failed for whatever reason. You want to go back and pick up the old data again. Or the system which is processing your data crashed. You want to go back and pull that data again from Kafka. You want to get that data from somewhere else. You want to get it from Flume, whatever you're writing to Spark from. So that's the reason you have a third piece, which is your ingest system. So your ingest system plus Spark streaming and an eventual store is what you want to use. So HDFS is the default, which is why I didn't put it here. HBase, Impala, things like that can be used to query the eventual output of this system and process it at some point. Now, these are layers that actually fit on top of these systems, right? You have data management, you have how do you manage your cluster, things like that. So you have like Cloudera Manager, Cloudera Navigator, Gazang, and all those things fitting in here. So those are different pieces which are not required, but make your job easier. Now, how do normal streaming architectures look? We talked about the components. We talked about Kafka. We talked about Spark. We talked about HDFS, HBase. How do they really look? Like, how does it integrate with each other? Is it just throw all of these things together and suddenly it starts working together? They all become self-aware? No, unfortunately. So this is sort of how it looks. This is a high-level, very generic overview of the system, right? Most often, people have highly specialized versions of this, but in most cases, this can sort of explain how it would look. There's always some data source which is producing your data. These data sources send it to some ingest system like Kafka or Flume. So now these systems are essentially buffers because whatever produces the data wants to send off its buffers, empty its buffers as soon as possible. The second set, which is your ingest system, is built to actually buffer data for a longer period. These things are designed to be like that. Like Kafka, if you have actually read Jacobs' blog, you can actually understand why I'm saying that. So it's actually a distributed partition storage system. You can essentially store data as long as you have hardware to support it. Now, once you send your data in there, you could use Spark streaming to pull the data out from those systems and process it. Once processed, you have some form of output, which you could essentially send it back to Kafka or an ingest system and have that data be available to applications directly. It's a very popular way of doing metrics, doing alerts, right? So you have a whole lot of data coming in from millions of sensors. Now, what happens is these sensors send in data which don't really mean anything by itself. Think about it in this way. If you have temperature sensors across a bunch of places or weather sensors across a bunch of places, just taking one sensor and reading its data is usually not useful. It just says, oh, it's this hot, right? It doesn't tell you, it doesn't give you information about patterns. It doesn't give you information about what could be changing over a period of time in a larger area. So now you have a bunch of sensors you're getting the data from. You're getting data for a longer period of time. Now you process that, and you send it. You say, oh, this is stuff that has to be archived. Let me archive it to HDFS. You write out to HDFS, but then you see this one thing which could be a problem, right? One thing which could which was the result of that processing, that could really mean that somebody needs to get a pop-up on his desktop somewhere, or a call on his pager or mobile phone, right? So that stuff would be sent to Kafka again. Now, once it's sent to Kafka, you have these applications which poll Kafka to get these alerts. So you have an app that's sitting and polling a queue to get a specific alert. Oh, is there a P1 issue somewhere in your cluster? So that alert can be pulled out from your by the app and posted to a dashboard, or force your ops guy to get up in the middle of the night. So this is sort of how generally things look like. You want to have archiving and you want to have forwarding to other apps. Now, again, you want Kafka rather than direct forwarding, because Spark streaming is not built to buffer stuff. Spark streaming is built to process stuff. So you push the data out and have it buffered elsewhere in case your application is not pulling out the events in real time. You don't want your application sitting and polling Spark streaming to get data. More importantly, Spark streaming doesn't have a server that will serve data out. It basically just writes out the data to some eventual store like HDFS or HBase. So anybody have questions about this before we move forward? Okay, I'm going to go ahead. So, Spark is this fancy system that everyone wants to use these days. There are reasons it's fancy, there are reasons everyone wants to use it, but in the simplest form, this is why it is, right? Like, one of the most important things which I've seen is Python, right? Like, people love Scala, people love Python. If you can support both of these things, yeah, you're probably going to get a good audience. The second thing is that it's actually very easy to develop. You don't have to think about it in terms of map and reduce. You have this pretty large API which sort of helps you understand how your application is processing the data, rather than take your data, take your algorithm, convert it into map reduce, right? So the more important thing is that you have a good API that allows you to develop. It becomes faster for you. The very simple reason that Python became so popular is that it is pretty simple to use, right? It's the same story here. The API is easy to understand. It's pretty simple to use. And with data frames, it's becoming even simpler. If you want to use SQL, you can actually write it out directly in your application, right? So that's one of the most important factors why Spark became so popular. Spark streaming basically inherits all that from Spark. So this is sort of how a Spark application looks like. I'm assuming most people who have used Spark sort of understand how this looks, right? So there's a driver, which is actually what is executing your application, the stuff that you wrote. Now, the APIs actually translate into distributed calls, which process the data in a distributed fashion on individual workers. Now, these workers actually process these individual pieces of data and say, hey, I'm done, and sends a pointer back to the results. Not the actual results, pointer back to the results to the driver. And the driver applies the next operation on those results in parallel again. And then you have all of the shuffles and things like that internal, which basically moves the data around the cluster and process it in a distributed way. So this is sort of a simple way of looking at a Spark application. Drivers your point where application is processing the data and running your application, and the processing happens in the workers. Now, the core of Spark is the RDD. RDD is the data model of Spark, right? So every piece of data you want to process in Spark is represented as an RDD. So RDDs are basically just data sets which are distributed and they're completely fault tolerant. Each RDD is immutable, which means that you could take an RDD, apply a bunch of operations, get a new RDD. Every operation really gives you a new RDD, but assume you apply a bunch of operations, eventually you get a new RDD. Now you want to apply two different operations on this RDD, you don't actually have to regenerate the whole processing chain all over again. You basically take the RDD and you apply both operations separately and get two resulting RDDs. If you cache this in memory, the data is not even reprocessed, right? It's sitting in memory. The processed version of the RDD is pulled out for processing in two different cases. So that is one of the reasons that Spark is extremely fast. When you're doing a whole lot of processing, you don't actually have to go and read your input data all over again. You can start from the last common point in the tree. So the reason I'm talking about RDDs is because RDD is going to be the most important piece of the next data structure we discuss. So before we go to the data structure, quick overview of what Spark Streaming is. Spark Streaming is actually written on top of Spark as a library. So Spark Streaming actually is not different from Spark. To submit a Spark Streaming app, you do the same thing as you do in a normal Spark. In a normal Spark app, you do the Spark submit, and you say, hey, yarn cluster, yarn client, standalone, or whatever, and then you pass in your application and its parameters, right? So it's the same story. You use the same APIs. You use the same command line interface to actually submit your application. So if you use the Spark Launcher app, it's the same thing. The Spark Launcher library uses the same, you submit the application the same way. Now, when you submit it, you get the same benefits of using Spark, which is the fault tolerant, scalability, and high throughput, because Spark Streaming is actually built on top of Spark. How does Spark Streaming look, right? So Spark Streaming's core is what is called the dstream. Dstream is the Spark Streaming data model. Dstream is actually built on top of RDBs. So what does a dstream look like? A dstream actually doesn't have a single look-like thing. At any point in time, dstream looks different. Why? Simply because you are getting more and more data in real time. Rather than RDB, where your data is static, your data is not static in a dstream. Your dstream is actually pulling data out of an ingest system at any point in time. So now, how does a dstream look like? Basically, think about a dstream as a bunch of RDBs, right? A system that is continuously generating RDBs. That's what dstream does. So what a dstream does is, say I'm pulling data out of Kafka, and you set the batch interval to be 1 second. Let's discuss what a batch interval is in 1 minute. But assume it's 1 second. What it does is every 1 second, it basically goes in, reads all of that data which was pulled out of Kafka, generates an RDB. And then whatever operations you said you should be applying on that dstream, it goes and applies it on that RDB to generate a processed version of the data. So you get processed data right after that 1 second. So instead of getting processed data continuously, you get processed data every batch interval. So the batch interval is essentially the time when the data which is received from the previous n seconds is processed. And you can configure it through a command line parameter or the Spark configuration. This is sort of how it looks like. So see that 0 to 1, 1 to 2, that's basically the batch interval multiplier for the batch interval. So initially there's some data which is generated at RDB at time 1 and at time 2, 3, 4. This brings a question, right? Like, what's the point of just getting a bunch of RDBs? The interesting thing is that most often, I'm not generalizing here, but I have supported a lot of customers in production. Most often, people actually don't have historical data lookups in streaming application. They just want the current data and apply a bunch of processing in real time on it, right? They don't usually want to say, oh, take all my data which I received in the last 2 years and apply this operation on it. That's usually why archival storage is required. So now what happens is this kind of processing basically allows you to process your data as it comes in and write it out to HDFS, HBase, whatever in real time. So how does a microbatch work? Like, what happens during a microbatch? This is what basically happens during a microbatch. You sort of write the code to process your microbatch or like this. There's hashtags there. I don't know if it's clearly visible. But basically what happens is you're applying a bunch of operations on your initial RDB, so on your initial dstream. So if you do this, you get a stream that reads off of Twitter. And then you're applying a bunch of operations to get the tags from the Twitter stream. And then you're getting those tags and writing the tags out to HDFS. That's simply what this piece of code does. I don't know if it's useful, but somebody might have a use for it. The advantage of doing this rather than having all the data getting written out to HDFS is that you don't actually have to write everything that's coming in your Twitter stream. You're only writing the tags. So now you could simply do this. At every batch interval, you apply the flat map operation and get the status, update get the tags out of that status, and just write the tags out to HDFS. Now you have accumulated tags for the last 1 year. You can apply, who's popular, Donald Trump versus Hillary. So that kind of operation basically is what you sort of use Spark streaming for, right? You eliminate what is not required, streamline your data, write it out to archival storage, and use that data to process, apply stuff over, your processing over the last 1 year, 2 years, how much ever you want. So earlier I said you don't want to do a lot of historical data thing with Spark streaming, and I said that I sort of like, but in truth, you can actually do that too. So because Spark streaming fundamentally depends on RDDs, it is possible to actually take a bunch of RDDs which were generated in the last window of time and apply an operation on it. So if you want to say, okay, take these two streams and select all of the users who logged into system A and system B at the same time. So think about Playtika, right? They want to see which users played the poker game and which users played this game. I don't know what this game was. Bingo Blitz. In the last 2 hours. Are they playing it at the same time or a different time? So things like that are sometimes useful. I don't know if it's really useful for Playtika, but as an example, it's pretty useful, I guess. So you want to take analytics, you want to take information and combine them for a period of time. That's actually possible in Spark streaming. So in Spark streaming, you would basically say, hey, get me a window of time. So what happens is Spark actually just creates an artificial window on all the RDDs which are generated. This window keeps moving forward. So the window of streaming doesn't actually do anything. It basically just says, oh, at this point in time, my window had all of those RDDs. Now, if you have those RDDs, any operations you apply can be actually applied to those RDDs, which means that if you have 2 days worth of data you want to apply your analytics on, you can do it. So window streams is actually incredibly popular. The reason I told you that you shouldn't be using it or you shouldn't need it is simply because of the fact that window stream is actually a resource-intensive system, because of the fact that at some point, even if you're not actually storing this, caching the RDDs, you still need to get that data from somewhere. So either you're keeping the RDDs around in memory, so you're keeping the entire window of RDDs in memory, or you're keeping it on disk, right? Like RDDs can, contrary to popular belief, RDDs can actually go to disk. So now, you're going and using some resources somewhere, so you want to keep your windows as small as possible. We had a customer who asked us if a 1-year window is possible. I said, yeah, sure, 1-year window is possible. Just make sure you have enough money to buy that many machines to keep track of all the data, right? So instead of that, you don't want to do 1-year windows here. 1-year windows can be done in your Spark application, which is running on actual files in HDFS. HDFS is meant to do stuff like that. Store data, right? That's HDFS's job, not Spark's job. So let HDFS do its job. You're talking about Windows, you can talk about 1 hour. That should be fine because you don't want to actually write down to HDFS and read it for every hour, right? So for, oh yeah, I want to figure out who logged in the last 1 hour, that's perfectly fine. So when you use window streams, just be aware of how much how much processing can be done. If you're making a command line parameter, if that thing is more than like 2 hours, throw an exception. The interesting part about Spark streaming is that Spark streaming is itself running as a Spark job. So it is not actually, there's nothing secret about Spark streaming in terms of the API used. Any API that Spark streaming is using is pretty much a standard API in Spark. There are some hidden APIs which are internal, but most of those are not used directly. Like there's code that accesses the block manager. Most often users don't need to access the code, block manager. But submitting apps, submitting data, processing it is all done by Spark in the exact same way a user's app would do. Spark streaming runs as a a Spark job. Spark on Yarn has security. As a corollary, so if you run this thing on Spark, Spark streaming on Yarn, which is secured by a Kerberos KDC, you will get the security in your Spark job. So you can actually do a K-init and run your application or pass in a key tab and use that key tab to process the data. So even on a secure cluster, you can actually run a Spark application and a Spark streaming application. The third one is actually a pretty interesting point. You could essentially reuse data, reuse your code, which you wrote to do your archival storage processing thing in Spark streaming. Because, like I said, Spark streaming processes RDBs. if you're processing RDDs elsewhere, make it a library, put it into your POM and dump it onto the cluster. Use the same libraries and it works fine. And you have custom systems which you wrote internally, right? There are a lot of people who write custom systems which are internal to your company. In that case, you could always write a receiver to pull data out. I will tell you why a receiver is not a particularly good idea, but if you want, if you want the shortest path, usually writing a receiver is the shortest path. So how do you share code between Spark streaming and Spark? So let's assume you have this library which basically looks at your log lines, pulls out all of the errors. Now it assumes that all of the log lines are in the RDD here. So you may have read it from HDFS or something. And you have an RDD of strings. It basically applies an operation saying, hey, does this contain the keyword error? If it does, return it, right? So now you have an RDD of string which is all of the error lines. Now you can take that and do whatever you want with it. You can write out HDFS, throw an alert or whatever. Now, how do you reuse this code in Spark streaming? In Spark, it sort of looks like this. You read a text file, you filter the errors, and you save it as a text file. In Spark streaming, you basically read that off of Flume or Kafka or whatever. This changes based on what system you're reading off of. And then you apply the same thing in the for each RDD. So now, for every RDD that is generated, the same library which you use to just process your RDDs is called to process your dstream data. Now, you could write that out as text files. Now you have your errors written out as text files in real time rather than going to HDFS once, then pulling out and writing it again, right? So this kind of stuff is actually very useful for Spark, for users who are using Spark streaming, because you can't always migrate from Spark to Spark streaming today. But you could always reuse your code and show a POC to your boss and then have him approve it to migrate. So before we go into Kafka, a quick word about reliability. Assuming all of you read this wall of text. A quick word of reliability is that Spark streaming isn't 100% reliable in certain cases, simply because of the fact that the system that sent the data actually has to be able to replay the data if Spark streaming has to be reliable. So now, what Spark streaming does is, as it receives the data, it keeps track of it, and eventually at the end of the batch, it processes it. The problem is failures can happen between the time you receive the data and the time you processed it, right? So that 2 seconds, if your driver fails, now you have a problem. You lost all references to your data. If you lost all references to your data, you sort of lost your data, right? Because your driver is the only thing that keeps references of data. It's okay if executors go down because it's replicated, but if the driver goes down, you lost the data. So what do you do? So if you are using a system that can replay the data, you can always replay the data from that system. Spark also has an option of having a reliable distributed log, right? Spark uses a log which is written out to HDFS, so by itself it's distributed. And what happens is any data that is written, it first persists to that log and then sends it out for processing at the end of 2 seconds. Now when the data comes in, it sends, and the persist is complete, it sends an ACK back to the system that sent it so that that system can get rid of the data if it has to. So now doing this has an advantage in the sense that you will not lose data on driver failure. And that ACK piece is especially important because it is possible that we didn't write the data into the HDFS wall and we failed before that, in which case you still need to be able to read it from the system that sent it. So there are 2 pieces that's important. The first thing is that a reliable receiver can only read data from a system that itself is reliable, that itself has a way of sending an ACK and saying, hey, I have actually completely stored this data. You can go and get rid of it if you want to. Now, the second one is actually enabling your wall. So a write-ahead log has to be enabled. All you need to do is to set this parameter to true, and it works out of the box. Now, anyone familiar with Kafka is going to say, no, that's a bad idea, right? Kafka does exactly the same thing on the Kafka side. Why are you doing it again? Like, you shouldn't be doing the same thing Kafka does. And Kafka is a system that's meant to do this. Spark is not even a system that's meant to do this. So why are we doing it? Because Spark is not simply stuck to Kafka. Spark doesn't depend only on Kafka for ingest. You could pull data off of Samza, Kinesis, things like that. So Flume. Not all of these systems have a way of replaying the data which has been hacked. Kafka has a way of replaying the data which has been hacked if you know the offsets, but not Flume, not other systems which generally give you the latest data when you code, right? So for those systems, this is still important. If you're using Spark streaming with Flume, you would have to do this. So the reliable Kafka-The stream actually does the same thing. It basically creates a receiver. The receiver keeps calling Kafka, pulls out data every 2 seconds, sends it to process. Now, I said you can write receivers earlier. I also said it's a bad idea to write receivers. Why? Well, if you don't have an option, go ahead and write receivers. But if you can design something that doesn't need receivers, you should probably go that way, because every receiver actually takes up a slot on an executor. Because a receiver runs as a Spark task. It's a long-running task. So you have one executor sitting there doing nothing all the time. It's not actually doing nothing, it's receiving data, but it's not processing it. So now that is actually a waste of resources if your data is like, you're receiving data, but the data received is actually slow, but you have a lot of processing to do. So you probably want your executors. So in that case, receivers are actually a waste of a resource, right? It's a waste of that one executor, even though you could avoid it. Now, again, that's one piece. The second thing is that if you're using a receiver, how do you parallelize receiving data? Receiver runs as a single task. How do you parallelize it? There's no direct way in Spark to parallelize it. If you want to parallelize it, what you have to do is to create as many receivers as you want and have that pull data out in parallel. So you see the parallelism is explicit from the user. So you either take it as a command line parameter, hardcode in your application, read it from configuration somewhere, but you have to basically create n number of receivers in your application code. There's no way for Spark to say how many receivers you need. You have to say how many receivers you need. It's sort of tricky because you're not always do you want 100 receivers running. Usually what happens is you have code which is meant to handle peak, right? But your peak is only about 3 to 4 hours a day. It's not your entire day. Think about when peak is. Peak hours is usually 9 a.m. to noon or like 5 to 7 in the evening. And you don't always have data coming in at the same rate as the peak. So if you over-provision your receivers, you're wasting a bunch of resources, even if you have stuff like dynamic allocation enabled, right? You have dynamic allocation enabled, dynamic allocation will kill your receivers, kill your executors only if they're not being used. Guess what? A receiver is sitting and using an executor. Even though it's not doing anything, then there's no data being received. So at that point, your dynamic allocation is not helpful to you. You're not saving any resources which you could have used for another app. So in the general case, you want to avoid receivers if you can. So the reliable Kafka-The stream actually has a receiver which runs on exactly one node, and then it pulls out the data from Kafka. The problem is this creates a lot of network traffic to that one machine, in addition to all of the problems which I just mentioned. So stuff like these are interesting problems to solve, and Spark community has actually solved this one problem. So Spark has a way of not using receivers for Kafka. So, this is one of the other things that I forgot. I already mentioned it, but even if you use a reliable receiver, you have to use the wall. And with Kafka, the wall is overkill. They're doing a double write because Kafka has already done that write on its site for. So Kafka is actually a reliable log, right? It uses, it actually keeps track of it by storing data in files. So you are essentially taking a data from a reliable log and then storing it in another reliable log, which seems like a waste of resources. How do you actually store, how do you actually get away from these problems? The solution is fairly simple if you think about it a little. Kafka has the concept of partitions, right? Each topic is a partition. Each partition is always going to sit on a single machine. Now, if you know that, and you know that RDDs also have partitions, you could really be smart about it. Well, the community, there are people who are actually smart about it. The interesting thing is that if you know that you can actually partition your data exactly as it is partitioned in Kafka, Do you actually need to run this one node that keeps processing the data? No, you don't. What you do is you basically parallelize your pulling out of data from Kafka too. So that's exactly what Spark does. At the beginning of every batch, it says, hey, the last batch which I received had offset n. Offset is a way of keeping track of messages. Think of it as an index, right? So you have n messages. Your next index is n plus 1. So the last batch I had offset n. So this batch I'll start reading from offset n plus 1 and read all of the data from there. Now you can read all of the data from there, process it, and write it out to HDFS or whatever. Now the interesting part of it is you still have to pull this data out from Kafka. Instead of doing a receiver, what would you do about it? What we do is map a single Kafka partition to a single Spark partition. That Spark partition, at the end of a batch, goes in, pulls out all of this data from Kafka, and then processes it on the same machine. So rather than triggering a shuffle every now and then, the partitions are mapped directly. So it pulls out the partitions as it comes in. So it pulls the data from each of the Spark partitions, pulls the data from Kafka, processes it, and writes it out. So it happens in parallel. Now, you can always have all of the messages which are remaining pulled out, or you could have a subset of them pulled out subject to a maximum rate. So you specify the maximum rate and you pull it out as is. Now, the interesting aspect of this is that recovery from failure doesn't need a write-ahead log in Spark, because every RDD, you know two things. What is the starting offset? What is the ending offset, right? If you know these two things, you can always get that data back from Kafka without actually storing it locally, which is exactly what Spark does. At the end of the processing, when a checkpoint is written, it writes out the RDD. That RDD also has information about what its starting offset was, what its ending offset was. Now, if you fail, if your application fails, your driver fails, it restarts on a different node, all it needs to do is to read that checkpoint back from HDFS, find out the last offset, and read from there, instead of actually having to read a wall and figure out what is processed. So that is exactly what we recommend that you do with Kafka. So in Spark 1.4, this was not considered stable, but at Cloudera, we actually tested it. We tested it against real clusters, automated tests against real clusters every day. We found this to be extremely stable, in fact, more stable than the reliable Kafka receiver. And we recommended this in production back in CDH 5.4, which is a couple of months ago. So if you are actually thinking about choosing Kafka and Spark streaming, this is the way to go. You don't use the reliable stream. Eventually, that's going to go away when people say, hey, let's deprecate and remove this. Now, this is the way you want to process data from Kafka. In fact, if you already have code that uses reliable stream, using this is actually just one-line code change. It's only changing from from where you say create Kafka stream, you just say create Kafka direct stream. It's actually like adding like 5 letters. That's it, 6 letters. It's fairly simple. You don't actually have to do a whole lot of code changes and things like that. Just do that, deploy your application. You don't actually change any API calls, nothing. Just that one line of code and you're done. Now, a lot of people ask me about exactly once processing. Well, I don't really believe in exactly once processing because of exactly that reason. There is no exactly once processing. You can go and read academic papers which actually will prove the same thing for you. They'll actually take this and reduce it to a problem that's in NP complete or something. But the basic idea is the same. There is no exactly once processing because it's almost always going to be almost exactly once processing. In presence of failure, you cannot do exactly once processing. You can do exactly once processing if you know that there's no failure. You have a system like a database that's going to assure you of something. You need asset semantics to actually do that. And because of that, you can't actually do exactly once processing in Spark and Kafka, right? But you can do almost exactly once, which you can do only with the direct stream and not with the reliable Kafka stream. Like I said, at the end of every batch, there's an RDD which is generated. The RDD has the starting and ending offsets. Now, to do exactly once processing, you could actually write some code to keep track of the starting and ending offsets of each RDD. So now, if a failure happens, you don't even have to depend on the checkpoint because checkpoints are notorious for anyone who has used Spark and upgraded Spark, you know that. checkpoints are not reliable through upgrades because of the simple fact it uses Java serialization. Java serialization breaks if you upgrade your code. The moment you recompile your code, Java serialization will break. If you upgraded Spark, your Java serialization will broken. So you want to actually store this information elsewhere. Zookeeper is a good place. You're interested in storing it in Oracle? I don't know. You could store it anywhere you want. You could write it out onto your local disk. So these offsets can be persisted, and once these offsets are persisted, you can use that information to simply restart from where you left off. This actually guarantees that the processing happens exactly once in most cases. Now, why I say most cases is because of the 4 edge cases I could think of in about 20 minutes, right? It's fairly simple to think about it. Fairly simple to figure out if there's a problem here. Most cases, you're going to write it out to HDFS. Guess what? HDFS is not ASIC compliant. So in the middle of your write, your network could die. You don't know if HDFS actually wrote out the data to files or not. You could have renames to keep track of stuff like that. But that's another story because there are a bunch of things which is not atomic over there as well. Because you could actually do the rename operation could fail because your network went down. You will end up writing the data all over again because you don't know if your data was written successfully or if the rename operation failed. God knows, right? So you have to write it out at that point without manual intervention. You could always have your ops guy go and look for the file and figure out if it's closed correctly. But if you don't want to do it without manual intervention. Now, there is also the other aspect of you write out the data to HDFS, you rename it correctly. Now you're writing the offsets out to your MySQL. Guess what? Your machine died. You forgot to write out the offsets because the machine died. So at that point, you still will have duplicates. So these are these edge cases which you could really cause, which could cause duplicates. But they are rare enough to actually be okay in most cases. The best way to avoid duplicates is to keep track of your data by having IDs, universal IDs, UUIDs. You don't have to have like a massive ID. You could be very smart about it, be optimal about it. Use, when you're generating your data, you know how you're generating your data. Have your machine name plus an atomic int or something, and be very simple about it too. But have IDs. It's the simplest way to avoid duplicates, right? Don't rely on systems that are not ASIC compliant to generate process data without duplicates. If you use something like this, you could always use a key value store to figure out if you processed your data or not. So have some form of an ID, and your app would be resilient to duplicates. That's exactly what you want to do. Yes. So the question was if there are any performance improvements. So in our simplistic testing, we didn't actually do a whole lot of testing, but in our simplistic testing, we did see that the direct Kafka-D stream actually has better performance. We generally attribute it to 2 things. One is that your data is not being read by a very small subset of machines. Your data is actually being read in parallel on several machines, which is also the reason for the second one, which is that when you have a single machine reading all of this data, your number of machines available for processing, executors available for processing is reduced. And if you want to read enough data, you need enough receivers, which reduces the number of executors available for processing in general. So if you're doing anything that is not merely word count, you will probably see an improvement in performance. Depending on how much data you're reading, that will change, right? If you're not reading a whole lot of data, it probably won't change a lot. But if you're reading a lot of data, then you're probably going to see a difference in performance. So I can't give you exact numbers because I don't know, but you're more than likely to see a reasonable, visible performance difference if your scale is large enough. Now that we talked about the internals and how stuff works internally, what are the general use cases we see? So this is actually a snapshot of Cloudera customer use cases. Usually Cloudera customer use cases we have seen is a pretty good reflection of like the 90% of the community, of the users using the system. We are not talking about 100%, we're talking about 90%. We're not talking about Facebook and LinkedIn and all those guys who have very different use cases than the normal customers. We're not talking about people who are running 10,000 node clusters. We're talking about people who are generally running somewhere in the low hundreds, high hundreds to the low thousands in terms of cluster sizes. So in those cases, these are generally the ones which we have seen. I actually talked about one of these use cases at Spark Summit earlier this year. So that was actually a use case at Salesforce. So it's pretty similar to what we see over here. So most of them are real-time dashboards. Real-time dashboards also include alerts. So I'm not specifying alerts out as alerts out separately, but it basically shows approximate results. Think Google Analytics, right? It says, hey, in the last 1 hour, this is an approximate number of things that happened, number of metrics that changed, right? But your actual results will be available after n hours. The reason being that there is delayed data. There is data that may not have, that actually came in that last 1 hour, but did not make it to the processing while the dashboard was being generated. So approximate results dashboard is a pretty common use case. Alerts is a pretty common use case. This is reconciled eventually, maybe an hour. It used to be 24 hours when MapReduce was around, but now people tend to do it 1 hour, 2 hours because Spark is actually much more lightweight to run. So periodically, it's reconciled with actual source of truth, Spark, and then you have your real data and your current data. Think about it in terms of how you see, if you're familiar with it, Druid. Druid does something similar, right? It has approximate results for the last n minutes or so, and then it combines it with the actual results, which happened over the last n days or something, which you're keeping track of. Joins of multiple streams is another aspect of this. This is a very popular one. This is sort of what I talked about at Spark Summit too. So think about it. It's one of the most useful things in, say, fraud detection, or you want to figure out if this user's account has been compromised. Think about it. If this user's account was logged in from Los Angeles now, and 2 minutes later logged in from Kansas City on a different system, it's either that that person's using a VPN and using Kansas City IP address, or the account has been somehow the account has been compromised. So information like that is usually useful because you have sort of a window in which you can decide whether an account has been compromised, and not necessarily over a single stream of data, but over several streams. And now the other aspect of things is that RDDs, which are created in real time, being reused in a pseudo batch form. This is something very common because Spark Streaming still doesn't support data frames, right? So if you use data frames, you sort of need the RDD model to process it today also. So which is why the third one is sort of becoming popular. But eventually, data frames will come to streaming as well, at which point I would delete that line from it. Now, what else is coming? I don't know how many of you downloaded the Spark 1.5 preview release. So Reynald posted a preview like 2 days ago or 3 days ago, which is a preview of Spark 1.5. It's going to be available in a couple of weeks, 2 to 3 weeks, depending on how long testing and things like that. What is coming? The first one is better monitoring and alerting, right? So alerting is something you'll have to build on top of the monitoring aspect, but there is more monitoring coming. This is one of the things that Spark didn't think about early enough, but now monitoring and alerting has become sort of important to figure out what's happening with your application. So there are new web pages, there are fancier graphs which you can see. So you can sort of figure out what's happening in more detail, stage-wise, task-wise, and all that. SQL and streaming is sort of like a medium to long-term thing. People are talking about it, but no one's actually implemented one, which is really good. So there are a bunch of implementations, I think, but there is currently none that Cloudera supports. But eventually, I think in the medium to long term, SQL and streaming will come. And who doesn't love Python, right? Python, limited availability, limited support is already available. So if you download Spark today, PySpark has limited Spark streaming support. Not all systems are supported. There is no real way to write a custom PySpark receiver and things like that. You have to write it in Scala, then write a Python wrapper over it. But there is limited support available today. So if you want to try out the Python part of Spark streaming, it's already there. Machine learning is something that lot of people have been interested in building models using streaming data. Today, there is a very limited amount of it available. There's a limited number of algorithms already implemented. More is coming. There are people contributing these as and when required for them. Like we don't actually have, we don't have an understanding of what people need. So most people tend to tell us, or they contribute themselves. So if you have a specific algorithm, a specific algorithm that you want to implement in Spark streaming, either you can implement it or let the community know, and there will be 10 others who probably want it. Somebody's going to implement it. Now, this is sort of how does Spark look as a community, right? There are 400 plus active contributors in Spark. There are about 320 pull requests open at any point in time. That only increases because the reviewers cannot keep up with the number of contributions that come in. Now, the number of companies actively involved is around 50 companies, right? They're not necessarily actively involved in the sense have one person on payroll doing this, but they generally have someone who knows something about Spark and they are contributing something to the Spark community. Databricks, Cloudera, Intel, Huawei, Yahoo, these are companies who actually contribute regularly to the Spark upstream community. Number of production deployments, Cloudera itself has seen dozens of them. We have a number of production customers who are running heavyweight jobs in Spark and Spark streaming. And Spark streaming recently survived the infamous Netflix chaos monkey. So they basically throw a bunch of failures at the application that's running. So Spark was, in this case, Spark streaming was running, and they basically go and kill random processes, random machines, and during specific phases and things like that to figure out if this thing can survive failures. And in the end, they were pretty happy with it. And it's included in CDH. So if you download CDH, you start getting this for free. Here are a bunch of links to the docs, but I'm fairly sure Google can give you more links. That's pretty much it. If you have questions, you can ask me now. So the question is, how reliable is Kafka, right? Reliable is a very, very overused term. So let me quickly define reliable before we go ahead. So reliable, when I talk about reliable, is I put 100 messages in Kafka. I have a guaranteed way of knowing if those 100 messages were persisted completely in Kafka, right? So if they were not persisted, I would somehow know that it wasn't and I need to retry. Rather than every time I put messages, I will know. It will be successful. There will probably be cases where it won't. But I would know if it failed. So yes, Kafka until recently had a reliability problem where you could actually trigger certain sets of failures and cause Kafka to lose data. Most of those have been fixed. So today, in most cases, like I don't know any edge cases off the top of my head which could actually cause Kafka to lose data. They have a lot of work going into fixing it in such a way that you wouldn't lose data. So there is a lot of code that went in to fix the replication system to make sure that you won't lose data without you knowing that it's not being written. So there were edge cases where you think that data is being written to all replicas, but guess what? Two of the replicas failed. It's just written to one replica. You could essentially lose data if that one replica died. Those have been fixed. There are ways of saying that, okay, write to at least n replicas, right? So there are ways to actually keep track of these things, which are configurable. So as you increase the reliability aspect, you're going to lose out on performance. But Kafka can actually be very reliable. Cloudera. Cloudera. So the simplest answer to that is actually Cloudera because I work there. So the reason I say Cloudera is that we actually support Kafka, we actually support Spark, we actually support the entire Kafka, Spark, HDFS, all those pieces. Confluent does support Kafka, I believe. I don't know if they have actually announced support yet, but eventually they will. It's sort of obvious that if you're a Kafka company, you'll support Kafka. But they don't support Spark. They don't support HDFS. So if you want to, have 5 companies work through your support system, sure, why not, right? Like you have one person supporting one piece and the other supporting the other. Like we had this case where, we had a customer who was running Cassandra with DataStax, and they were using Flume, which is Cloudera, and suddenly Flume stopped writing to their DataStax system. They come to us, we're like, no, that's a DataStax problem. It's a Cassandra issue. They go to Cassandra, DataStax, say like, oh no, that's a Cloudera issue. It's a Cassandra, their connector going down. The eventual piece was we didn't write the connector, Cassandra didn't, DataStax didn't write the connector. It was something they picked up from open source. That was the one which is bugged. So, before they realized that whole thing, it took 3 days. Do you want your system to be down for 3 days? No. So in general, I would say go to one company who can support as much of what you're using as possible. If you're going to 3 different places, you're more than likely to see them pointing fingers at each other and saying, it's their fault, it's not ours. Yes?
Do you have the ability to learn smart streaming with using data frame and features?
So the question is data frames, tungsten, Spark streaming. So no. So currently it's on the community roadmap, but I'm sort of sure that there's not a whole lot of work happening today. But that isn't to say that it will never happen. Simply because it's open source. There could be some company who's actually built this internally, and tomorrow they'll announce it open source. But there's nothing happening in the community from a community standpoint. I know that it's happening eventually. It's not happening today. People want it, just that no one's implemented it. People don't want it that bad until it's happening. Yes. Yeah, you could do that. You could always do that, right? But so the question is whether you could just take the RDD and convert it into data frame. Sure, you could always do that, right? But you don't. So the advantage of data frame is this nice little API that you can apply SQL on without worrying too much about what is underlying. Now in Spark streaming, you're going to use data frames on top of the RDD, which is being generated periodically. You cannot say, okay, apply this on a window operation or apply a join on these 2 RDDs in SQL, right? You won't be able to do that. So you have to have streaming sit on top of SQL sit on top of streaming to actually do all that natively. So there is some advantage to having a streaming data frame per se. Yes.
Are you aware of any public fire hoses? Like if you want to run around with Kafka and Spark, and everybody at your company is way smarter than you if you don't want to back. Are there any public fire hoses that you could connect with?
So the public fire hose, so the question is whether there are public fire hoses. The most popular public fire hose is the Twitter one. So you get sort of like, I think a 1% or a 0.1% for free. Like you just need a Twitter developer account or something, and you can sort of access the Twitter fire hose for free. That's the only one I know of which is available publicly. So because Twitter actually allows you to pull data off of a fire hose, off their fire hose in real time, but none others I know of. It doesn't have all of the data you would get if you pay Twitter, but you get, if you want to just try out stuff, that's good. Yeah, you could compromise your company's security for sure. Yes. Yes.
So we, where I work currently have Flume, use Flume quite a bit. We're thinking of using that as source for Spark streaming. So, do you see any advantages of switching over to Kafka?
So this is basically a Kafka versus Flume question. Generally, I look at it this way: is is Kafka only used for feeding HDFS or Spark, then you really don't need Kafka. You can use Flume, you can use any other ingest mechanism. Kafka's benefit comes from the fact that you can feed several systems at the same time. So if you're going to feed multiple systems at the same time, you should use Kafka because you can send it to other applications also in real time. If you're only using it for Spark streaming and your ops team has a good idea of how Flume is working, how to keep track of Flume's metrics, whether Flume is crashing or not, you should probably just keep using what you're using already. So the biggest problem in terms of any of these systems is the ramp-up time for developers as well as ops is pretty high because these are not appliances. These are custom systems that run on a random box somewhere. So getting to know how it behaves in your environment takes time. How much of a support you have, how much, Cloudera, Confluent, Hotworks, any of these things, any of these companies, they'll be able to support you, but getting your system ready for your use case, you're going to have to go through the POC and then figure out if it actually scales enough and then deploy it, right? Is that cost worth it is the more important question. If the cost is not really worth it, just go with what you can understand, what you know works in a certain way. Just go with that.
So you mentioned that one advantage of Kafka is the sentinel workloads destinations, but Flume does the same thing, right? With multiple sinks.
Right. The difference is that Flume does a push model. So you have Flume pushing the data as it comes in, while your applications can't necessarily handle all the data coming in at some incredible rate. So that's why Flume is primarily meant for writes to storage systems or archival systems rather than to other applications. You generally want your applications polled for data when they are being used.
And I think that's why actually another department use Flume to push data to Kafka.
Right, that's a pretty common use case. I've seen that quite a bit because Flume is incredibly great at receiving data from a lot of machines and then just sending it downstream. That's pretty much what, we have customers who receive data from 600 nodes onto 5 Flume boxes. So that actually is really scalable. That is where Flume is really good at. And if you're writing to HDFS, all the 5 can write to HDFS directly. Instead, if you have multiple places to write to, you could put Kafka in the middle. That's sort of what's called Kafka. That was the initial way how Cloudera said that's sort of how we want to use Flume. And Flume is, Flume is a managed consumer and a managed producer. If you think about it from a CDH Cloudera perspective, because if a Flume node fails, if a Flume agent fails for whatever reason, Cloudera Manager will be able to alert you, restart the agent, and things like that. Well, if you write an application of your own, you have to have, monitoring on that. You have to make sure that it's running fine. While CDH Flume will actually be taken care of by Cloudera Manager. Yes. I think systems like Kafka should sit outside of Yarn, simply because there's no real way to. So Yarn is a resource management and scheduling system. When you're using Kafka, you're not really managing any resources, neither are you doing scheduling. You're going to use up all the resources available because you're actually buffering data. And you're not doing any scheduling because it's not actually processing data, it's just keeping data around. So I don't see any benefits of using Yarn. I don't see benefits of using running Kafka on Yarn and Mesos or any of those systems. But there is some activity in the community in running Mesos and Yarn, Kafka on Mesos and Yarn. And this is happening in the Kafka community, so they know what they're talking about. So if you follow that conversation in the community, you'll probably be able to figure out why that's happening. I don't see much of a point, but I don't have that much insight into Kafka either. Okay, so I think we're done. Thank you.